So I just want to remind you too, this is probably going to be the last time I do the warning, but I do it just about every video just at the beginning of the semester. This is going on my YouTube channel, as you know. So if you're, in hiding or don't want someone to know that you're taking this class, you might want to change your username to just like maybe your first name and your first letter of your last name. You might not want to show your picture, all that good stuff. And also you might want to let me know so that I can make sure in the future none of that comes by. Not that I think you have any desires to hide or anything like that, but just I just want to make sure I never get anybody in trouble.
Yep, sounds good.
All right. Okay. Well, I will also start off by telling everybody that Chapter 20, uh, in general at TCC, when I got here, we didn't generally cover quote unquote Chapter 20. Specifically, we had chosen not to cover the second law of thermodynamics. I say we, the department, had chosen not to cover the second law of thermodynamics, but that was before I got here, and therefore I wasn't part of the department. So I've been every semester teaching a little bit of 20, just because I can't justify covering any of thermodynamics if I'm not going to at least talk about the second law of thermodynamics. So I cover it in a very, very light way. To be honest with you, from the sections that we cover, I'm going to go ahead and read all the sections from the book and let you know exactly what's relevant to me. Uh, the section 21 is called 20-1 is called the second law of thermodynamics, an introduction. And in fact, every version of the second law of thermodynamics in this book is a version that you need to know of. And I mean, know of in the sense that be able to identify it as a version of the second law of thermodynamics, because there might be a question, and there often is a question, like on a test or a final exam or a midterm or something like that, where I ask, select all of the first law of thermodynamics, and it'll be like a whole litany of things listed, and then people have to go through and click every one, or if there's just one, they just click one. Same thing with the second law of thermodynamics. There might be a whole series of multiple choice answers, all of which, or most of which, are some relevant law of physics, so it's very easy to get tripped up a little bit, but your job would be to find exactly which ones of those are the second law of thermodynamics. So what I recommend you doing in the entirety of chapter 20 is every time it states the second law of thermodynamics, go ahead and write that down verbatim and what they call it. So all of those are quote unquote fair game for my tests. That being said, as far as my homework goes, I don't mind you skipping any of these sections that I say I'm not going to test you on, but I sort of do often expect you to do the homework for them. But again, I try to pick out the homework in such a way that it's not really onerous or difficult topics. So in section 20-1, as I said, it's the second law of thermodynamics. They just introduce the probably the most sensible version of the second law of thermodynamics, or the most mundane, and that is that heat spontaneously flows from a hot object to a cold object. And spontaneously means it does it on its own. You don't have to do any additional work to make it happen. Then we go into section 20-2, and we cover heat engines in general. And I cover that basically to give you an idea of exactly what a heat engine is. I don't cover all the different ones. I pretty much just, I'll mention the different heat engines that exist. There's a Stirling engine, there's an OTTO engine, there's the engine that we use most often, for instance, here is, darn it, I just lost the name. I was just literally thinking about it. Carnot's engine, Carnot. So the Carnot engine is one we'll cover, and that's mostly what I need you to know about is the Carnot engine. And then there are, refrigerators and air conditioners and heat pumps and stuff like that. Pretty much you need to be able to calculate the efficiency of those, whether they give it to you in terms of heat output, heat input, input, energy output, work done, all that kind of stuff. That's pretty much the main thing from this chapter that I think is fair game is your ability to calculate the efficiency. For any particular heat engine, as well as for an air conditioner, which in that case it's there's a different name for it, as we'll go over in a little bit. Same thing with air conditioners and stuff like that. We'll talk about entropy, and I want you to have some idea of entropy as a measure of disorder. And entropy in the second law of thermodynamics is section 20-6. 20-5 was entropy, 20-4 was refrigerators, air conditioners, and heat pumps, and 20-3 was Carnot engines, reversible and irreversible processes. And that reversible and irreversible process is probably the most important part to understand about heat engines and the things that we're doing with them. In section 20-7, we talk about order to disorder, and they gave you a really excellent example of how entropy and order and disorder are related. Then section 20-8, they talk about the unavailability of energy and the heat death of the universe. 20-9, they give you another excellent description of a version of entropy that is just amazing. So that's probably the most important part if you're interested in going on to study physics is, or any branch of engineering that really needs to understand thermodynamics. This last statistical interpretation of entropy is probably the most important part about that. But again, if you're not going into physics, or if you're not going into a branch of engineering that is heavy on thermodynamics, then it might not be as critical to you. Section 20-10 is thermodynamic temperature, third law of thermodynamics. That's covered in the sense that you should also know the third law of thermodynamics, which you can read in the book. So just make sure you have that written down and, of course, committed to memory. Ideally, when you're committing these things to memory, you want to commit them to memory such that you could verbatim give them back. But the more important thing is that you understand them well enough that you could paraphrase them. Just, of course, there's dangers in that. But if you have any particular paraphrase that you want me to run over and see if that's consistent with the actual definition, I'll be glad to do that for anybody. Section 20-11 is thermal pollution, global warming, and energy resources. I am trying my best not to discuss anything that could bump against politics in the lecture. So, global warming is obviously, for some reason, global warming seems to be a political problem. So I won't discuss it too terribly much. I will let you know that a couple of things. For instance, I have done my due diligence in the global warming area of science because, at one time, for instance, I also thought it was possibly BS. But one of the textbooks I have, for instance, that I wanted to make sure I had read a couple textbooks and worked through problem sets and stuff like that, so that I had a real understanding of what global warming says and all that good stuff. This textbook was a really good and short one. Notice how short it is, but it's by David Archer, Global Warming: Understanding the Forecast. I'll just tell you that one brilliant quote in that is pretty much what I think is almost all you need to know. I'm going to have to paraphrase it because I don't think I'm going to be able to find it on the fly like this. But basically, what Archer says is that we create, are these the people the climatologists that study climate, they create these global circulation models that predict, giving certain inputs, they predict what the temperature will be like in the future. That's not the only thing they're predicting, but what they're doing is predicting a bunch of different things, and one of the outputs is the global temperature. And it does seem that these models all point to the global temperature increasing over time. So I'll tell you the one amazing quote that he has in here is basically that every GCM ever created, and therefore that goes through all the rigors of testing of a GCM. Everyone, once it's accepted as a GCM that goes through, that has passed all those tests, everyone predicts global climate increasing, global climate temperature increase when you feed it the projected CO2 outputs. So it seems to reason that if we can do anything with global circulation models that is even remotely correct, then they're all telling us specifically that the globe is warming and that we are the major cause of that. We have certain experiments that we've done and certain tests that we've made that show that. For instance, like one of the biggest things, and this is one I've only heard on the BBC, NPR, and Skeptic's Guide to the Universe, which is a podcast I like to listen to, or I used to listen to. I listened to it for about 10 years, and occasionally I do now. But basically, that smoking gun type of evidence is basically that if the global CO2 concentrations that we're dealing with right now are mostly due to anthropogenic sources, meaning we're using fossil fuels, then because these fossil fuels are from fossils that died literally millions of years ago, the carbon 14 has completely disappeared from those CO2 molecules. So we're getting all this carbon from burning fossil fuels, and all this carbon should be completely without any carbon 14. And lo and behold, when we actually test the gases in our atmosphere, it turns out that a huge percentage of the CO2 production, or a huge percentage of the CO2 in our atmosphere, is in fact completely depleted of carbon 14, so that it points to somewhere in the excess of the upper 80% to the middle 90% of all of the global warming being a result of anthropogenic sources, in other words, us burning fossil fuels. So I'll just tell you that that's sort of the major evidence. If you want to look for a really good scientist that knows their stuff about global warming but doesn't necessarily believe, quote unquote, the hype, it's Judith Curry. She's pretty much the only one, and I'm not. Sometimes she says things that bothers me a little bit, but by all means, she knows more than I do, so I can't put her down any more than that. I'm just saying sometimes it says things that seems counterintuitive and counterlogical, but the vast majority of people are in contradiction with her, but she doesn't seem to acknowledge, or she doesn't not say that the globe is warming. She just says we're not necessarily in control of, or in complete knowledge of how much is due to us, and that she's not necessarily sure that it's completely a bad thing. I think I sort of sensed that out of what she was saying, and that she's not certain that we as a government or any government should do anything about it to prevent global warming happening. So I see some evidence of that as well in some of her statements. But check her out. I follow her and Michael Mann and various other people on what used to be Twitter or X. So let's leave it at that. And I apologize for taking even that long. So let's go back to now discussing chapter 20 dash, or excuse me, chapter 20, which is called the second law of thermodynamics. The chapter opening question says fossil fuel electric generating plants produce thermal pollution. Part of heat produced by the burning fuel is not converted to electrical energy. The reason for this waste is A, the efficiency is higher in some heat if some heat is allowed to escape. B, engineering technology has not reached the point where 100% waste heat recovery is possible. C, when converting heat to useful work, you cannot avoid producing waste heat. This is a fundamental property of nature. D, the plants rely on fossil fuels, not nuclear fuel. And E, none of the above. So, as always, you're supposed to read these chapter opening questions and take a guess or preferably a thoughtful hypothesis of the answer, and then wait for it to be answered as you're learning throughout the book. So as always, you should do that. That is very good pedagogy, or good educational practice. So the second law of thermodynamics, and the reason we need it is this. The first law of thermodynamics, I think you probably figured out now, especially if you've done all the homework from chapter 19. The first law of thermodynamics is basically a statement that energy is neither created nor absorbed, or destroyed. Excuse me, I don't know. I said absorbed. Energy is neither created nor destroyed. I will have to put a caveat on that with regards to relativity. When Einstein came up, literally like the day after, with an addendum to his special theory of relativity, he writes back and says, "Oh, by the way, I discovered this neat little thing: E equals mc squared." That E equals mc squared was a huge, huge deal. In fact, it's a major part of the reason that we were able to make nuclear weapons, which obviously have pluses and minuses, but one of the big pluses was that we were able to get out of the war probably a little earlier with a lot less life lost as a result of that. Even though obviously we there was a lot of life loss. So that was one of the cases. But the bigger case from the science standpoint is that we really had no mechanism for understanding at all how the sun could possibly work and still exist because Lord Kelvin had done a calculation assuming that the sun was burning the most efficient fuel source that he could imagine, which at the time was coal. So we knew exactly, or pretty accurately, what the weight of the sun was, and he imagined the sun was burning coal, and he worked out how long that sun could continue burning coal without running out, and I think the estimate was around 50,000 years, which was fine because until then, pretty much our record of our historical record was really the Bible. So when you look at the Old Testament and you go through Adam begat such and such at such and such an age, and he begat such and such and such and such an age, and so on and so forth. If you add up those ages at each of those begats up until you get to a person that exists at a time that we know in history, specifically at the time of Nebuchadnezzar, once we get up to there, then we can work backwards and figure out what the date of that Saturday was when God breathed the breath into Adam, and from that you get on the order of well under 10,000 years. So the 50,000 years that Lord Kelvin had predicted was quite good and quite relaxing because it gave us a sense of we still have a lot of time. But in the intervening period, we were starting to discover that there was an idea called plate tectonics, which made some sense because not only do the continents and more specifically the plates themselves, they fit together like a puzzle, and that was pretty impressive. But we could detect their motion, and it had to be very, very slow. And if it was very, very slow, that might mean the Earth would have to be hundreds of thousands, if not millions of years old. Then we also started noticing that when you put that puzzle together, the parts that were originally next to each other, or at least were next to each other at some point in time, have very similar species existing, even though now there's a huge oceanic gap between them. And life of the type that we're talking about oftentimes could not make such a swim or anything like that. And that pointed to evolution, and that pointed possibly to, again, hundreds of thousands, if not millions or billions of years of existence. So we were running into a conundrum. We had the plate tectonics, we had the evolution, and we had the burning of the sun. All of those looked like they were in jeopardy, but luckily Einstein comes along with E equals mc squared. A lot of the experiments being done at the time with the nuclear part of atoms was mostly being done in Germany. So him coming up with that E equals mc squared and publishing it all of a sudden meant that the Germans, who were the major power to be afraid of at the time, among others, but they were the major ones, uh, they might have had a head start on us on making a nuclear weapon, and that was what drove Oppenheimer and all the people that worked for him, including Enrico Fermi and all those people. So if you've seen the recent movie Oppenheimer, you'll know a little bit of that history. So, anyways, this was a really really big deal. But like I said, the first law of thermodynamics is just a statement of conservation of energy, and now that Einstein brought in E equals mc squared, we can't just say conservation of energy. We have to say conservation of mass energy because mass, in some sense, can be created or destroyed. It can be created from energy, where initially you just had a certain amount of energy, and all of a sudden that energy disappears. But now we've got a amount of mass given by the energy divided by the energy divided by the square root of the speed of light, or excuse me, the square of the speed of light. And similarly, mass can disappear and become energy given by m times the c squared. So we can't any longer say energy is conserved or mass is conserved. We have to say mass energy is conserved because we know that they go back and forth. Not only that, this is kind of a weird thing that everybody should know, but literally every time energy is created, it equates to a change in mass. So, for instance, if you took a gas tank, let's imagine a perfectly clean car with perfect technology, so that we could inspect anything we wanted to any number of decimal places. Obviously, there's some problems with being able to do that, but if you imagine taking a certain amount of fuel in a brand new car. So you've already cleaned out all the exhaust system, all the fuel system, and all that stuff. So all the gas that we're getting ready to put into this clean, pristine tank is going to be accounted for easily. If you put in, X number of gallons of gas in that car, and then you run it a certain amount of miles or whatever, if you then weighed all the exhaust that came out from burning those gases and you had a very good measure of the mass of that gas that you put in the car. When it was all done, you would find out that the mass of all the gas that was put in was in fact larger than all the gas that was collected from the exhaust and that sort of thing, seeming like Priestley was wrong, specifically seeming like some of the mass had actually been destroyed. And in fact, if you take the amount of mass that's been destroyed, in other words, the difference between the two masses, if you take them and you multiply them by the square of the speed of light, which is 180, or excuse me, 299,792,458 meters per second, if you square that, multiply it by that missing mass, lo and behold, you'll get exactly the amount of energy that was created by the gas. So it literally happens at every level. So hopefully that is something that's interesting to you. But the main thing is, again, we're going to say the first law of thermodynamics is a statement of conservation of, let's say, mass energy, even though it's really just talking about energy. But here's the neat thing, and your book shows a nice little photograph of this. If you take a coffee mug, now this is not a good one because it's a coffee mug made out of steel, so it doesn't break, but imagine a porcelain or ceramic coffee mug filled with coffee. If it were to fall off of a table and shatter in a bunch of pieces and coffee spilled everywhere, that would obviously be a bad day. But oddly enough, if you just have the first law of thermodynamics, there's no violation in the first law of thermodynamics if you make the argument that no, actually, what happened was I was sitting here and I was looking at this wet spot on my floor, and then all of a sudden the wetness and moisture in the carpet started shooting up into the air. The glass pieces that were all in little shards started jumping up into the air and coming together in exactly the right way that they're supposed to. And the coffee ended up right inside of the glass, and then the glass flew up and landed on top of my desk. Uh, that's completely allowed by the first law of thermodynamics. Therefore, we knew and we know that something must else be at play, and that something else is, in fact, the second law of thermodynamics. And the second law of thermodynamics, according to the Clausius statement, is heat can flow spontaneously from an hot object to a cold object, semicolon, heat will not flow spontaneously from a cold object to a hot object. Okay, that's the first law of thermodynamics. And you might think, wait a second, you said heat will not flow spontaneously from a cold object to a hot object, but what about your air conditioner, or what about your refrigerator, or what about your freezer? Your air conditioner or your freezer or your refrigerator actually literally pulls heat out of a cold space, the inside of the refrigerator or the inside of the freezer or the inside of the house in the case of the air conditioner, pulls it out and distributes it out to the outdoors in the case of the air conditioner, or into the kitchen in the case of a refrigerator or freezer. But be advised, that is not a violation of the second law of thermodynamics, because you can certainly do it, but it's not doing it spontaneously. And in fact, if you left your refrigerator unplugged for a month, you would certainly find that your electric bill went down a little bit. And that's where we were able to actually suck heat out of a cold area and blow it into a warm area. We had to do it by wasting some energy, specifically energy we bought from the electric company. So hopefully that helps a little bit. Now, in order for us to make better sense of this, we are going to study a heat engine, and a heat engine is any device that changes thermal energy into mechanical work. For instance, the steam engines that we ran trains with, they are heat engines. The automobile engine is a heat engine. However, an electric motor is not a heat engine, though it may have parts to it that run on heat and are heat engines, but generally speaking, an electric motor is not a heat engine. So that's why we're sort of getting embedded with we're actually coming up with not only the second law of thermodynamics, but we're also going to start talking about heat engines for some reason. And that this is why, because one of the ways we can test the second law of thermodynamics is we can see exactly what way and what things need to be done to extract heat from a cold area and to produce it out into a warm area. So we already have our Clausius statement of the second law of thermodynamics. Again, heat will flow spontaneously from a hot body to a cold body, and heat will not flow spontaneously from a cold body to a hot body. Now, the classic diagram for a heat engine is the following. So I'm going to go ahead and share my iPad screen in a second here. I almost said forgot, but that's why I had to say it out loud before bad things happened. So let me go ahead and share my screen with you real quick. This is the iPad. Take about a second to click in. So this should pop up any minute now. There it is. So a heat engine you can think of as the following. You can sort of say a heat engine is a thing that can take heat from a warm reservoir, okay, from a warm reservoir, and this is temperature TH. So heat is going to flow from this red thing. And remember, heat is energy in motion. It's not energy. It's not something that a thing can contain. It is the energy in motion. So basically, it's the amount of energy that went from one thing to another. Now, we're going to say the temperature of this heat reservoir is TH, and it'll be connected to a heat engine, and it's connected via this sort of pipe mechanism, if you will, so that heat is coming into here, and that heat is called Q sub H, which means the heat added from the high temperature reservoir. Now, inside of this engine, which we can represent, say, with a purple box, I'm going to say the engine is this right here. I didn't really want to go that far. Let's kill that. I'm going to go down to this far. And then what we see is this pipe that brought in the heat is going to actually get out a certain amount of work, which obviously is a helpful thing for an engine. And this amount right here is going to be called the W. But as you can see, the pipe got smaller. So obviously some of that W came from QH, but the rest of that heat went out as waste. So this is the engine part. I'll write it sideways. So there's our engine part right here. And out pops this, and it runs, in fact, into a cold reservoir. And this cold reservoir is at a low temperature. T sub cold. So, or let's call it T sub L. That I think that's what your book used. I use T sub C. Yeah, TH and TC. So the temperature of the hot reservoir is TH. The temperature of the cold reservoir is TL. And as I said, there is a amount of heat. In this case, it's going to be Q low. Q sub L that is going to escape and go out to the environment. So if you're talking about, for instance, a car engine, you can imagine the heat reservoir as the inside of your piston where the explosion occurs of your gas. If you're talking about a gas engine, basically a spark plug fires at just the right time when there's a maximum compression of the gas so that it sparks a fire. There's a huge explosion. That explosion pushes the piston down. That piston going down is able to push through a series of rods and things in such a way that the drive shaft can rotate, go into a differential, and then turn either the front or rear or both sets of tires and wheels, turn them to make the object go. That's the work part, is that piston pushing the rods, causing ultimately the tires to rotate. That's the work part. And then the extra heat that's left over is kicked out of the exhaust, out through the exhaust from a port in the actual cylinder, and that's what the QL is. Whereas the low temperature reservoir in that case would just be the environment. So wherever you're driving the car, it could, in principle, be inside your garage, but that's also a recipe for an accidental death by carbon monoxide poisoning. So let's not do that. But either way, that's what a heat engine does. It takes a certain amount of heat and converts part of it to work. And we'll learn that that's another law of thermodynamics, of second law of thermodynamics. Another version is that there's no way in which you can turn 100% of any heat into work. Okay, it's almost like there's a heat is like a bastardized version of energy, in that it's not as high a quality as mechanical energy. So, for instance, we can convert 100% of kinetic energy to potential energy, and we can turn 100% of potential energy into kinetic energy, and we can turn that kinetic energy into kinetic energy of rotation, again, 100%, right? But when you go to switch from heat, or from energy into heat trying to do work, then it turns out that it's not going to ever be able to be 100% efficient. So that's another version of the second law of thermodynamics, which we'll clean up later. That's not one you want to commit to memory. I'm just telling you that's what it is, and you'll see the other ones as we go. So if we look at this heat engine, we have some idea what it is. With this, I should also point out that the QH is always greater than zero, and the QL is always greater than zero, and the work is always greater than zero with this diagram. So you've got to see it as heat coming in is positive, and then that's the QH specifically. The work being done by the engine is positive, and then the heat being sent out of the engine is a positive amount of heat and being sent into a cold reservoir. And from this, we can discern very specific things. I'll tell you also, your book takes a bit of time to explain to you a steam engine and internal combustion engines. I highly recommend you reading that. This is where the knowledge comes in, where when you meet someone that's been doing physics or engineering for a long period of time, they can talk extemporaneously on topics of thermal physics and stuff like that. And that mostly comes from life experience as well as from stuff they've learned in books and then seen in real life. So I highly recommend you reading that, as I recommend everybody read all their textbooks. But either way, it does talk about a four-stroke engine and stuff of that sort. And it talks about why delta T, the difference in temperature between two reservoirs, is needed to drive a heat engine. But that's really the crux of it, is there's got to be a temperature difference. If the heat in the inside was the same as the heat in the outside, then heat can't transfer from T hot to T cold, or from T hot to T low, specifically because heat only spontaneously flows from a hot body to a cold body. And if they're the same temperature, that means no heat whatsoever. Now, now that we have this idea of what a heat engine is, this is where I'm going to explain to you the part that I think is relevant for you in my class, because again, I'm one of the only ones that actually covers the second law of thermodynamics. But what you look at is, in general, your book is using lowercase e for efficiency. And what I like to think of as efficiency is what you get, and I specifically mean what you get that's useful. For instance, you can get your car to move you along like you're supposed to with your internal combustion engine, and that's some of what you get, but you could also say, well, I like to ride on the trunk and hold my hands down by the exhaust pipe so that I can get warm from the exhaust coming out. And in that sense, you are making more use of the engine than you meant to. But what I'm saying here is what you get is really only what the engine's designed to do, and the engine's designed to make the car move. So the only part that's relevant for efficiency with a heat engine that's modeling a car is the work you get out, not the heat you get out. And then that's what you get divided by what you pay for. And that means the total amount of losses you have to incur to run it. So what you pay for. So that is a fundamental definition, if you will, of efficiency. Now, if you want to put it in the context of a heat engine, then I'd say energy is equal to the work part. Notice the W, that's really what comes out. And what it cost you is the heat that went in, and that, of course, is QH. Now, again, the job of the car manufacturer is not to give you a way to trap that Q8 or QL coming out of the tailpipe or anything like that. So we don't count that as part of it. But conservation of energy does tell us that QH has to be equal to Q low plus W. So in principle, you can replace QH or W with letters that you want. And in fact, what I'm going to do is solve for W, and then I will get that E is equal to Q hot minus Q low divided by Q hot, which again, this is just going to give you a actual decimal. If you want it as a percent, you move the decimal two places to the right and put a percent symbol in it. But the main thing is this is the efficiency. Now you can break that fraction up to 1 minus Q low over Q hot. And that is the efficiency of a heat engine. Now, if we're talking about something other than a heat engine, then work or QH might not be the two relevant parameters. But the main thing is for a heat engine, that is what the relevant parameters are. So we'll use that. And now I'm going to give you some examples of how to use it. So, for instance, we could say this is just like example 21 in your textbook. It says an automobile has a efficiency of 20%. So let's do this example. A car engine has an efficiency of 19.9%. Okay. And produces, let's say, 25,000 joules of work per second. What they want to know, what I want to ask you is how much heat input is required and how much heat is discharged as waste. Oops. And you could say it's being wasted, or you could say it's just being used to make the earth a little warmer. So that would be nice, which actually it does, no matter what, independent of the trueness of anthropogenic global warming or whatnot. So how much heat is wasted? I couldn't remember what word was there. All right, so let's go about solving this. What we know is that we are given 19.9%. So that's E equals, and notice it was given as a percent, so I'm going to go ahead and convert that to a decimal. I'm going to say that 0.199, and that, of course, is equal to the work done divided by QH. Now, we are also told that the work is 25,000 joules per second. So that's the same thing as saying 25,000 watts, but we're trying to work sort of per second or per cycle or something. So I'm just going to say that the work, which should be measured in joules, not watts, the work is 25 times 10 to the third joule. Actually, it's 25, yeah, times 10 to the third joules, which obviously only has, say, 2 sig figs. And what we do know is that QH has to be equal to W plus QL. So we might be able to use that as well. So for the first part, how much heat is required to be put into the engine? That's QH. And what we know is that since 0.199 is equal to W over QH, and we know W, then we can find that QH is actually equal to W over 0.199, which of course is 25 times 10 to the third joules each second divided by 0.199. So when I actually compute that, I'm going to say 25 times 10 to the third divided by 0.199, and that gives me 125.6 times 10 to the third joules each second. And obviously, I only had 2 sig figs on everything, so this gives me 2 extra sig figs. But we can now say that QH, the total heat input, has to be 125.6 times 10 to the third joules, and I'll circle that as the first answer. Any questions on that?
Nope, no questions.
Yeah, pretty straightforward, right? Now we can use the other part, QH equals W plus QL, to figure out what heat is wasted. So if we take QH, because we know it, actually I should probably continue writing in purple since that's what my solution is supposed to be in. We had QH is equal to QL plus W, so that should give us QL is equal to QH minus W. So with that, I can say QL, the wasted heat, is going to be 125.6 times 10 to the third joules minus, now the work we said was 25, and that would be 0.00 times 10 to the third joules. Both of those were per second, but the main thing is we're just talking about joules right now. So we have 125.6 times 10 to the third minus 25.00 times 10 to the third. So that's obviously going to give us a little bit under 100. Oops, excuse me. A little bit under 100 times 10 to the third joules. So I'm just going to say it's approximately 100.0 times 10 to the third joules. And of course, with this arithmetic, you know that that digit nor this digit can be significant. So now we know what the wasted heat is as well. Any questions on that, Matt?
Oh, pretty straightforward.
Yeah. Good deal. All right. So now that you have that as an idea, it's really good to sort of see what we're trying to get at with this. So, one of the main reasons we're studying this heat engine and the reasons that we did some of the things we did with processes in thermodynamics in the previous chapter is so that we could actually analyze a Carnot engine and, in so doing, find some relationship between a heat engine and the second law of thermodynamics. So, I want to explain a little bit how a Carnot engine works. And like I said, your book has other engines uh, and other books have other engines as well. In fact, you can find old engineering manuals on internal combustion engines, and they actually talk about these same models. But Stirling is one you've probably seen. You might have even seen a Dodge product with the name Stirling on it. That's partly where it came from. Is the idea of the Stirling model of the engine. There's an Otto, OTTO, which seems to me like was probably the origin of the phrase automobile, but I have no idea. I've never found that listed. But it is odd that it's Otto, OTTO, but it's spelled so differently. The main idea, though, with each of these ideal engines, and they really are supposed to be ideal, what the deal is you're trying to make a heat engine that is as efficient as possible. So in order to do that, we make all the processes reversible, which more or less says you can't have any friction and stuff like that. And then with reversibility, you get sort of the best case scenario of how efficient an engine can be. And then if you find the efficiency of that engine, and someone claims the efficiency is something higher, then you know for a fact that someone has made up something or made a horrible mistake in the process of trying to calculate the efficiency of that engine, or more likely they're just lying. Okay. So the Carnot engine consists basically of four processes. So what I'm going to do is I'm going to take a P versus V diagram. So I will try to use my good writing and nice shape tools from my iPad to do this as well as possible. So the pressure is going to be on the vertical axis, and the volume is going to be on the horizontal axis. And what I'm going to imagine is two uh, isotherms, so two pressure versus volume combinations that occur at a single temperature. So I'm going to do it with a dotted line. So we'll say that's one isotherm, and that isotherm happens to be at a temperature TH. And the word I'm saying, just in case you can't tell from my hick accent, is isotherm. Okay. There's another one as well that's going to correspond to a lower temperature, and this one shall be called TL. So that is again an isotherm. So what's going to happen, as I mentioned to you, was that we're going to start off with a isothermal compression. So an idealized Carnot engine consists of four processes done in a cycle, two of which are adiabatic, two of which are isothermal. In this first case, I'm actually going from point A, which is the on the isotherm TH. So we're looking at something going on here, and it's going to go from A along this isotherm. So I'll put an arrow this way so you can tell which way we're actually going. Now, because of that, you see that this is an isothermal expansion because the actual gas volume is going up. That's why it's going to the right. And that's an isothermal expansion to the point B. Now, the next part is from B, we're going to actually have an adiabatic expansion from B to C. So this is an adiabatic expansion. Now, what happens is because of the expansion, remember, in general, if you take a volume of gas and you allow it to expand, that is a cooling process. So that actually usually results in the temperature dropping. And we see that's what happened here, both in the isothermal case. Which didn't actually have a temperature change, but when it went from the isothermal TH to the isothermal TL, that was an adiabatic process where no heat flowed, yet it still cooled. So it cooled only during B to C. Now, after this, we're going to have a compression, and that compression is going to be isothermal. So we'll have a compression that looks like this, and that's from C to D, and that one is an isothermal one, which should be obvious now because it literally lies right along the isotherm that we labeled TH, or excuse me, TL. And then finally, the rest of the cycle is from D to C, and in this case, that's an adiabatic compression. So this one was an isothermal compression, and this is an adiabatic compression. Cool. And I more or less left a leg off of my N here. And I called it a M just N just now, even though it's a M. Okay, so this is the Carnot cycle. So Carnot came up with this idea, and in addition to it being this process, he makes the assumption that at each point it's only differentially away from an equilibrium point. That's sort of like a way of defining what a reversible process is. Basically, you can push it just ahead a little bit, say to compress the cylinder, and in so doing, at any point you could turn right back and go right back to the last line you were. And each of those individual points that you might stop at are in fact equilibrium points so that you can get. If they weren't equilibrium, you couldn't really graph them on a graph. So we're seeing from A to B is isothermal expansion. So that's the expansion where the temperature doesn't change, but the volume and the pressure drop, which you should expect, right? If the volume increases, you should expect the temperature or the pressure to change because of the ideal gas law, which mostly applies to all gases, right? So you expect that. In that case, though, it's only the volume and pressure that can change, not the temperature. Then we move from B to C, and in that case, the pressure decreases, the volume increases, and the temperature decreases, and that's from B to C, and that's the adiabatic expansion portion. After that, there's then an isothermal compression, and you might, in fact, imagine that as maybe the cycle in your engine where the exhaust gas is being blown out. And then the next part is an adiabatic compression. And in that case, a part of the reason why this adiabat or these adiabats can occur is it's really slow to try to have heat transfer from one object to another. That's a slow process where individual molecules from the hotter object has to run into individual molecules of the colder object, and that gives the colder object's molecules a slightly larger kinetic energy, but that isn't a slightly larger random kinetic energy. That's very much unrandom. So you've got to then wait for all those atoms to bump enough to where now all of the atoms have a net higher random kinetic energy. So as you can imagine, that's a very slow process. So when you're talking about an explosion of a gas in a gas engine or explosion of a gas in a diesel engine where you don't even have a spark plug, then you can expect it's going to happen so rapidly that very little heat is going to flow into the engine block as opposed to just pushing the piston really hard. So that's what the Carnot cycle is. I will tell you the big shortcut that we're going to use, and just because I don't want to go through the derivation, I don't want to teach you all that background material, though I highly recommend you read it and understand it. And if you understand it from this course, by the time you get to engineering thermo, you will be really, really well off in your thermodynamics course. So we already had that the efficiency of a heat engine is basically 1 minus QL over QH. So we would actually want to figure out exactly what's going on with that QL and QH. And really, the QL and QH can't do anything during an adiabatic process. So that forces us to understand that the QH must come in during the isothermal expansion. So this is QH coming in. And then during the isothermal expansion or compression, excuse me, out pops the heat QL. So that's when that actual process takes off. And of course, if we can know the QL and the QH, we can calculate the efficiency. But when we say the process is reversible, since, whoa, Nelly, I don't know what I even wrote there. Uh, I'll just say reversible turns out to mean that Q over T, Q1 over T1, say, is equal to Q2 over T2. And the reason why is this Q over T quantity is called the entropy. And entropy generally is always growing, is always getting larger. But in the case of a reversible process, it can stay the same. And you can in principle make it decrease, but it's going to come at the universe getting more entropy in general. So the total entropy of the universe is always quote unquote increasing, but you can have a little part of the universe where the entropy is decreasing, but that comes at the expense of much more entropy increase outside of that little system. But if we go on the assumption of knowing that, for instance, Q over T equals Q over T is true for a reversible process, then we can skip all the cool stuff that your author does to come up with this new formula for the efficiency. And all we have to do is replace the Q over Q with T over T. So we can say, for instance, if I call Q1 the QH, so we'd say QH over TH is equal to Q low over T low, then you could solve for QL over QH, and what you would get is QL over QH is obviously equal to, whoa, now is that right? Wait a second. QL over QH. Ah, yes, is TL. I was thinking I was getting it upside down, and I knew that wasn't right. So that's the big deal there. We're supposed to get that TL over TA, or excuse me, TL over TH, so that now we have yet another version of the efficiency for a Carnot engine. So I'll write Carnot here. We'll normally probably just put a C on it, but in this case, it's 1 minus TL over T hot. So this is a new equation that we have, and this is the equation that we still have that works for all heat engines. So we can use the QL over QH for all heat engines, and the TL over TH is sort of the best case scenario. So when we're actually calculating this Carnot efficiency, what we're finding is the goal of what we could possibly try to shoot for, even though we know darn good well we're never going to get it. But we could shoot for that goal, and we shouldn't shoot for anything higher, but not with that particular engine because it's just impossible according to the second law of thermodynamics. Now, that being said, science is science, so if I were to find an experiment that violates the second law of thermodynamics and someone could back it up, then I would be infinitely famous and probably win a Nobel Prize, and I'd be really, really happy and that sort of thing. So we always continue to look for such violations, but in general, I wouldn't spend a whole lot of time looking for violations of the second law of thermodynamics unless they're sort of neat little quirky things like the way conservation of energy and conservation of mass became, instead of two separate things, neither of which were true. It's one big thing that both of which is true. So anyways, now that we have that, we now have a formula for it, and that's what your book spends a couple sections of it doing. And in so doing, they get the same result that I have. Now, they did mention something as this process was going on, so I want to go ahead and read this quote to you. It says, all reversible engines operating between the same two constant temperatures, TH and TL, have the same efficiency. Any irreversible engine, so that means real engines instead of Carnot and Stirling and Otto engines, but any irreversible engine operating between the same two fixed temperatures will have an efficiency less than this. So that's the linchpin here. You can't say Carnot has anything to do with anything else until you have this idea that the any irreversible engine will automatically have less efficiency than the Carnot engine. And you can't have the Carnot engine being relevant unless you have all reversible engines operating between the same two constant temperatures, TH and TL, have the same efficiency. So hopefully that will help you a little bit. So now I'm going to go with uh, a simple calculation, another example. So a steam engine, let's look at this one. This will be another example. So, and it's only the second one. A steam engine operates between, let's say, 600 degrees Celsius, and I'm going to assume all three of those figures are significant. And let's say the other temperature is 330 degrees Celsius, again, assuming three sig figs. What is the maximum possible efficiency? And I'd say possible, but really it isn't possible because obviously the efficiency is always going to be a little bit less than that. So that's why I'm sort of hedging a little bit on that one. My Y turned out terrible. My F turned out terrible too. But anyways, I don't think y'all care that much about that. But the OCD in me just won't let it go away. Okay, so there we go. So this problem's pretty straightforward. We're going to use our equation for the Carnot engine efficiency because we know the Carnot engine is sort of the supreme example of any engine since all engines have the same efficiency that operate between the same two temperatures. So what I'm going to do is I'm going to say, oh man, I hate it when my iPad keeps doing that. So what I'm going to do is I'm going to say that TL obviously has to be the lower temperature, which is 330 Kelvin, or excuse me, 330 degrees Celsius. But to make that into Kelvin, we have to add 273 degrees Celsius roughly. So 273 plus 330 is 500. 600 would give you exactly that, 603. So this is 603 Kelvin. Notice no degree there. The T hot is in fact 600 plus 273, so that one's going to be 873 Kelvin. Again, no temperature, no degree mark in that one. So the efficiency E of the Carnot engine would be equal to 1 minus TL over T hot, which is 1 minus, in this case, you have to use 603 Kelvin divided by 873 Kelvin. And turning to my calculator, I'm going to do 1 minus, and what we have is 603. Let me double check my math. 273 plus 330 is 603. Yep, that's what I had. And now I'm going to divide that by 873. And that gives me 0.69407. In that case, remember we only had three sig figs and we're dividing, so really the 0 and the 7, the 0 and the 7 are not. But now I can take that and say 1 minus that, and we get 0 point to the proper number of sig figs is just 3093. And that efficiency doesn't have any units. It's a dimensionless number, but you see it's about 31%. So about 31%, that's what I'm going to say. So the maximum efficiency you'd ever expect is something slightly less than 31%. So E, steam engine, for this particular steam engine is definitely less than 30, or excuse me, less than, I would just call it 30.9%. And that's about it on that one. Does that make sense?
Yep.
Now, the other example that your book does is a nice little one where you can see basically a potential scam or grift, if you will. This is example three, is what I'm calling it. But in this case, we're basically trying to investigate a phony claim. So I'm going to say example three. And what we have here is uh, friend of a friend tells you about the engine he's designing. He claims QH, the heat input, is 9.0 kilojoules at 435 Kelvin. And QL is 4.0 kilojoules at, in this case, 285 Kelvin. Should we believe him? Okay. So the solution here requires our understanding of efficiency. And in this case, we need to see both efficiencies because we'd like to know what it is according to our calculation with just standard engine efficiency, which is E is equal to 1 minus QL over QH. But we also want to compare that to the Carnot engine, which should give us 1 minus TL over TH, or that formula should give us the Carnot efficiency. So if we find, for instance, that the Carnot efficiency is lower than the engine efficiency, then you know it's a scam, but or at least a misunderstanding of physics. So here's the actual efficiency in terms of the Carnot. So for a Carnot engine operating between 435 and 285 Kelvin, that's 285 Kelvin divided by 435 Kelvin. That subtracted from 1 is the Carnot efficiency. So I'm going to say 1 minus parenthesis, just to be careful here, 285 divided by 435, close parenthesis. In this case, I get 0.344. That's 3 sig figs, so I'll just add two other figures here, and this will be 83. So it's about 34.4% efficient. Is what the Carnot engine is. Now, the actual engine efficiency that he's claiming is just E, and that's given by now 4.0 kilojoules divided by 9.0 kilojoules, which is equal to 1 minus parentheses 4 divided by 9, close parentheses, and that gives us 0.5555. In this case, we only had two sig figs, so I'm going to say this is 6. And that is the efficiency of this engine. So he's literally claiming that the engine's more efficient than a Carnot engine, and that just can't be. So, any questions on that one, Matt?
No, no question.
Gotcha. There's another statement coming up here. This is called the Kelvin-Planck statement, and the Kelvin-Planck statement is basically that no device is possible whose sole effect is to transform a given amount of heat completely into work. No device is possible whose sole effect is to transform a given amount of heat completely into work. So, one way of interpreting that I think is particularly nice to see is when I draw a heat engine. That would be violating this principle. So if we start off with a hot reservoir, and these reservoirs, by the way, are supposed to be anything where you can withdraw heat and not have its temperature change. That's what we mean by these reservoirs. So, for instance, a lake. You could pull some heat out of a lake, and because the lake is so big, unless you pulled a huge amount of heat out of it, the lake temperature would not change. So in that sense, a lake is a heat reservoir. And I don't know why I just did this. I did it literally in the wrong color. So what I'm going to do is I'm going to take heat from a hot reservoir, and the heat I'm going to take from that is going to be at a temperature TH, and that heat is going to run right into my heat engine like this. And now my heat engine is going to be, oops, just like that. There's my actual engine. But here's the interesting thing is we're going to take this heat right here and make all of the work go out that way. And in fact, that is what we're violating. So the Clausius or the Kelvin-Planck statement. So what Kelvin and Planck are telling us is that it's not possible for every bit of the heat QH to be converted to work W. Uh, we have to have some amount of heat going to waste. So that's a whole nother version of the second law of thermodynamics, and I think it's a pretty interesting one. Seems kind of weird, but it turns out will ultimately physicists will take all of these and have since the time that they were made. All of these different statements of the second law of thermodynamics have been shown to be 100% equivalent to each other. So just keep that in mind. So far, we've learned two: the Kelvin-Planck statement, and the first one, which was the heat flows spontaneously from a hot body to a cold body. Heat does not flow spontaneously from a cold body to a hot body. So as I said, this is the example that should not happen from this Kelvin-Planck statement. A heat engine can't turn 100% of the heat that it takes in into work. I think that's enough for tonight. We've actually gotten through a good chunk of the chapter, and I like to get this done usually in a day. I think it's fine for me to spend the rest of the time to do the little bit of chapter 20 that's coming next. So the chapter 20 is still going to be due this for you guys. Y'all meet on Tuesday, so it'll be due this Monday at 11:59 p.m. Uh, and I think y'all be able to do that. I will cover some more material next time. So go ahead and have a good day, and thanks for coming. And I'll wait in case anybody has any questions. I'll wait for the last person to leave. So, Matthew, do you have any questions, or you need to split to your lab?
No, no questions from me, and I need to split.
All right, have
Thanks.
a
We'll
good
see you
one,
next
buddy.
time. Yep, you too. Thank you.
Bye-bye. All right, so no one else came in. I've waited to the 6:35 mark, so I know no one's trying to use it as an office hour. But here we go. That's it. Have a good evening, everybody. Next time I will finish out what I'm calling chapter 20. Like I said, a very shortened version of it. But have a good day. Bye bye.